Welcome back to The Explainer. Today, we're diving into a concept that literally bends the minds of even the most seasoned physicists. It's something that challenges our fundamental understanding of reality itself. I want you to imagine, just for a second, standing right near the edge of a black hole. You just hang out there in the quiet of space for, say, 1 hour. You check your watch, you turn your ship around, and you head back home to Earth. But when you finally land, you discover this staggering truth. Exactly 7 years have passed here. 7 whole years. That is the incredible hook of today's Explainer. We're looking at the actual, literal mechanics of time travel. And no, this isn't some fantasy born in a Hollywood writer's room. It's a provable, mathematical fact of our universe.
Okay, let's dive into this. Contrasting an hourglass ticking away a single hour with an entire planet aging 7 years, that feels exactly like the plot of a sci-fi movie, right? But the absolute most fascinating part here is that this is actual, verifiable science. Today, we're going to figure out exactly why time slows down inside the gravitational well of a black hole, and what that extreme environment means for the tangible possibility of time travel. Now, this whole concept seems totally counterintuitive to our everyday lives, but it was actually predicted by Albert Einstein over a century ago, and modern astrophysicists, they've completely confirmed it through rigorous observation. So to really grasp how this extreme time dilation works, we need to travel straight out into deep space and take a look at what we're actually dealing with.
Just as a quick refresher on the cosmic pipeline, we know black holes don't just, pop into existence out of nowhere. They require the spectacular death of a massive star. We're talking about a star roughly 20 to 30 times the mass of our own sun. These stellar giants, they burn incredibly hot and fast. And when all that stellar fuel is eventually spent after millions of years, the star detonates in a massive supernova. It is truly one of the most violent events imaginable in the universe. After that explosion ejects the star's outer layers deep into the cosmos, the remaining core immediately succumbs to its own immense gravity. It just starts compressing inward, violently folding in on itself. And it's that rapid, unstoppable collapse that ultimately leads to the birth of a black hole.
Now, the sheer, incomprehensible scale of that core compression is exactly where classical physics just starts to break down entirely. You're taking over 1 billion tons of mass. So picture entire mountain ranges or even small planets, and you're crushing all of that down until it fits into a singularity literally no larger than a thimble or the cap on your thumb. When you force that much mass into a single, microscopically small point, the gravity becomes absolute. It gets so unimaginably powerful that the required escape velocity actually exceeds the speed of light. And since light is the absolute speed limit of the cosmos, nothing can ever break free from its pull. Because absolutely no light can ever escape to bounce back to our telescopes, the object appears perfectly, utterly dark.
But extreme gravity is really only half the equation here. We know these objects exist, and we know their gravitational pull is absolute. So why does time actually slow down around that thimble-sized mass? Well, to figure that out, we have to look back to the year 1915. This is the year Albert Einstein fundamentally shifted our entire understanding of physics by introducing his general theory of relativity. Before this moment, gravity was largely just thought of as this simple magnetic-like pull. Einstein, however, was the very first to propose that gravity and time aren't just independent actors on the cosmic stage. No, they share a direct, intimate, and physical connection. The rule he gave us is profoundly elegant once you wrap your head around it. The higher the gravity in a specific area, the slower time will move in that area. See, before Einstein, the scientific consensus was pretty much that space was just this empty stage where events happened, and time was simply a universal clock ticking away consistently in the background, exactly the same for everyone, everywhere. But relativity completely threw that out the window and introduced this mind-bending concept, space-time. This is the idea that space and time are actually woven together into a single, unified, flexible fabric that stretches across the entire universe. So the really crucial takeaway here is that when gravity exerts its pull, it's not just tugging on physical objects or bending physical space, it is actively pulling, distorting, and warping time right along with it.
And this brilliantly illustrates how it all works. Think of a large backyard trampoline as that space-time fabric. If you were to take a super heavy bowling ball and place it right in the center of that trampoline, the stretchy material immediately sinks, right? It stretches downward, creating this deep, curved dip all around the ball. Well, out in space, this is exactly what's happening. A massive, incredibly dense object like a black hole sits on the fabric of spacetime and pulls it incredibly far down. Because space and time are inextricably woven together in that fabric, that deep gravitational pull literally drags time down with it into the curve. So for anyone or anything caught in that gravitational dip, the very passage of time is stretched out and slowed down, relative to the rest of the universe.
Now, it's easy to assume this strange phenomenon only happens near distant, extreme anomalies way out in deep space. But let's bring this astrophysics back down to Earth for a second, because we actually rely on real-world proof of this happening right above our heads every single day. Just consider the GPS satellites constantly orbiting our planet. Because they're out in space, floating further away from the Earth's dense mass, they experience slightly less gravity than we do down here on the surface. And because of that lower gravity, time on those satellites actually moves just a tiny bit faster than the clocks sitting in our living rooms. It's a microscopic difference, sure, but without constant mathematical adjustments to account for this precise time dilation, your daily GPS map would drift by about 10 kilometers every single day. You'd literally never find your destination, all because time in space is ticking at a slightly different speed.
Let's move to and see how this builds when we take that everyday GPS concept and scale it way up to the most extreme gravity in our galactic neighborhood. The math gets absolutely staggering. Right in the center of the Milky Way galaxy resides a supermassive black hole named Sagittarius A star. Astronomers have carefully calculated the gravitational forces at play there, and the resulting time dilation is just profound. If you were to somehow travel safely to Sagittarius A star, stand near its event horizon for just 1 hour of your own time, and then immediately fire your engines and return to Earth, the universe you left behind would have totally moved on without you. You'd come back to find that 7 whole years had passed for everyone else. Your friends, your family, they would all be 7 years older while you only aged by a single hour.
Now, if that specific scenario sounds eerily familiar, it's highly likely because you've seen Christopher Nolan's film Interstellar. There's that deeply heartbreaking scene where the main character, Cooper, travels to a water planet situated extremely close to a supermassive black hole. And because of the intense gravitational pull, completely warping the space-time around that planet, just a few hours on the surface costs him decades of Earth time. When he finally gets back to his ship, he watches a backlog of video messages and realizes his daughter has entirely grown up without him. The wild thing is, the filmmakers didn't just invent that scenario for dramatic effect. As the science behind the film proves, it wasn't just fiction, it was real physics. That is exactly how the universe operates when extreme gravity and time collide.
But here is the final, incredible twist that very few people actually realize. You don't need a spaceship or a supermassive black hole to experience this phenomenon firsthand. You are literally time traveling right now simply by existing on this planet. Just think about your body as you stand or sit right now. Your feet are planted closer to the Earth's core, which means they are physically closer to the planet's mass. Therefore, your feet experience slightly more gravity than your head, which is farther away. Because higher gravity equals slower time, the time at your feet is moving just a tiny bit slower than the time at your head. Now, obviously, we are talking about a difference measured in fractions of a nanosecond, so your shoes aren't going to stay eternally young or anything. But the difference is mathematically real, it is constantly measured by physicists, and it is an undeniable fact of relativity.
So, the next time someone casually asks you if time travel is possible, you can look them right in the eye and absolutely tell them you're doing it right now. Today in our Explainer, we covered the violent birth of black holes, how Einstein's space-time fabric seamlessly connects gravity to the clock, and we proved that you yourself are a localized time traveler. If you found this dive into astrophysics and space-time insightful, please go ahead and leave a like so we can share this with more curious minds. And definitely join us for the next Explainer, where we'll be tackling the famous Fermi paradox. We're going to look at the staggering mathematical probability that alien life exists and ask this highly provocative question. If the universe is so vast and so ancient, why haven't we met anyone else yet? Stay curious, keep learning, and I'll see you next time.